Hello students, welcome back. In the previous video, we established the concept of dimension. As a matter of fact, we did those through two previous videos. From the second video, we went through the concept of dimension and all those examples and whatnot. And in the third video, we proved the technical detail of the dimension lemma. This is a conclusion coming from the second video. We don't have to go to all those technical detail. Okay, we have various different descriptions or properties of dimension. Let capital V be a vector space and let vectors v1, v2, v3 all the way up to vn be a minimal set of generators of V, that is, none of its proper subset generate V. For example, this generates, yes, but if I select one of the vector and cast it out, then it's no longer a generator. There is a certain vector from capital V so that cannot be expressed as a linear combination of V1, V3, V4, V5, and then all the way to Vn if I exclude V2, for instance. Anything. As a matter of fact, there's no reason to exclude V2 as a matter of fact because you see, I can always change the order. So if I'm excluding, usually I'm excluding the first one or the last one without loss of generality. And that's an interesting concept, as a matter of fact, that we are going to be utilizing. Okay, all right. Let's begin proving it. The theorem said v1, v2, v3 all the way up to vn generate v. Okay, that already know. So we have to prove the linear independence. How to do that? Again, let's use the proof by contradiction. Suppose otherwise. Suppose that they are linearly dependent. In other words, there is a non-trivial solution, x1, x2, x3 all the way up to xn, not everything equal to 0, yet the linear combination x1 v1 plus x2 v2 plus all the way up to xn vn is equal to 0 vector. Okay, and then we can always change the order and then rename those. So without loss of generality, we'll say the first is non-zero. If first is 0 and then let's say 17th one is 0, we'll just switch the order and then rename those. Therefore, we can solve for V1 by this algebraic manipulation. Let's see, flip everything else to the other side and divide by x1 because it's okay to divide by any non-zero real number. So what did you get? V1 is equal to some linear combination of V2, V3 all the way up to Vn. And then what did you get? We found a proper subset, V2, V3 all the way up to Vn, that generated V1. And if you went through all those exercise sets of the previous module, all the homework set, then you'd know this generates entire V, but assuming you didn't, let's do. This part may be redundant if you already did all the homework problem, but assuming you didn't, and let's do that. Choose any vector from capital V. Because V1, V2 all the way up to V and generates entire capital V, you can write that arbitrary vector V as A1, V1 plus A2, V2 all the way up to AN, Vn, where A1, A2, A3, all those are real numbers. And then in place of V1, we're going to plug this one in. And then we do a little bit of algebraic manipulation. What do you get? You have linear combination of V2, V3, V4 all the way up to Vn. And what did you get? Arbitrary vector V of capital V is a linear combination of v2, v3, v4, all the way up to vn. Looks like I lost a addition symbol there. Let's correct the typo. And consequently, a proper subset v2, v3 all the way to vn, which is a proper subset of v1, v2 all the way to vn, generate v. Did you say this is a minimal set of generators? That's a contradiction. It's no longer minimal because even a proper subset generated it. So there goes a contradiction. So alright, if you have a lot of generators, then you can throw some away, and then trim it down until you get to the minimal generators. Then it's a basis. Alright? Next thing we want to do is the other way around. Start from linear independence. If you have just one vector, then automatically it is independent. If you have two, then linear independence is really easy to find. Unless they are collinear, they are linear independent. And then 3 vectors is a little bit harder because more to consider. 4 vectors are a little bit harder, getting harder, but still, you can go up. And the maximal set of linear independence is also a basis. And as for the as for number of generators, and then the number of linearly independent vectors, number of generators always has to be greater than or equal at least, you see. Number of generators also has to be greater than equal. Well, that's getting a little bit too deep, excuse me. Let's come back to the core point. Minimal set of generators. If you have a lot of vectors, then okay, it'll easily generate the entire V. But you can trim those down to make it more efficient. Down, we got to minimal. That's a basis. And also, linear independence. Okay, it's easy to get linear independent if you have very small number of vectors. But add more, and get more and more complicated system. Going up, and then we get to the maximum linear independence. That too is basis. So generators coming down, linear independence going up, and they merge at the same place, the number of bases or the dimension. Okay, let's prove this. Okay, this is maximal set of linear independence. Okay, we already know v1, v2, v3 all the way to vn is a linear independent family. We must show it generates, alright? Alright, how do you prove that? For arbitrary vector v in capital V, we want to get a linear combination of it. Now, let's get some trivial cases out. If that v happens to be just one of v1 or v2 or whatever, then there goes the linear combination, v equals to vi, and then everything else is plus 0 vn's, you see. Only one, and then all the others are 0. So there goes the linear combination. So trivial case, let's get it out. Suppose that v is not equal to vi for all I. Okay, that's the other case. Alright. Then just add one more, v, and you get a proper subset. So proper superset, excuse me, of v1, v2, v3 all to vn. Alright? If v is equal to some of these, then this is redundant, but that's already taken care of. So let's suppose v is different from all those. So add more, then this is proper superset. So this is not going to be linearly independent. See, this is maximal set of linear independence. So proper superset, so this is not linearly independent. In other words, we can find a linear combination that add up to 0 vector, yet not all of them is 0. Okay, that's what linear dependent is telling us. Now let's make one small observation first. This last one, x cannot be 0. What if this x is 0? I'll throw that away, then what do we get? x1 v1 plus x2 v2 all the way up to xn vn is equal to 0 vector. Then x1, x2, x3, all those xn, all those have to be 0 because we're assuming these are linearly independent. Indeed, x is 0, then this part drops out. This part drops out. So we get x1 v1 plus x2 v2 plus all there to xn vn is equal to 0 vectors. Excuse me, I'm misusing this 0 number and 0 vector constantly here. I'm sorry. And consequently, all the coefficients have to be 0, and that's a contradiction because this we assume that's 0, and consequently all these are 0. So yes, we just got this x cannot be 0. So we're going to solve for v and divide by x. Alright, solve for v, flip everything else to the other side, and divide by x. Yes, I can do that because if x is equal to 0, already got contradiction. So assuming x is non-zero, then we can always divide by x. And what did you get? This v can be written as a linear combination of v1, v2, all the way to vn. Yeah. Arbitrary element of v is generated by this set, v1, v2, all the way to vn. That's precisely what we wanted to prove. Linearly independent, we already knew, we already assumed. We wanted to prove the generation, and we just did that. So, what's the conclusion? Minimal set of generators, maximal set of linear independence, they merge at the same value, the dimension of the vector space.